Okay. Okay. Welcome everybody to lecture 27 of CSE 548, the analysis of algorithms. This is the last lecture of the semester. Let me start off with a few course announcements, okay, and then we'll get into some more technical questions. First, questions of various course announcements. The homework, the final homework of the semester is due today. Some people have not taken their extensions yet, okay, and they want to know, can they take it on the last homework? That's fair to take the last extension on the last homework, but get it in the TA's mailbox by Monday night at 11 p.m. so that it can be graded, okay? The graduate projects are due at 3 p.m. tomorrow. That's at donut hour, okay? So I want to see all the projects, okay, with my donuts, okay? So if there's any questions with that, let me know. Another issue with the grad projects is presentations. Now, I had said that all graduate students should do presentations. We've arranged 2 time slots for in this room when people can come give their presentations and be videotaped doing so. Okay, being videotaped, giving yourself a presentation is good practice. You look at yourself, you see what you're doing. Most of you will learn you don't look actually as bad as you think you do, which I think is good from a confidence point of view. Some of you will learn things like, let's say, nobody will be able to hear you, or nobody will be able to read your slides, like, for example, these. Okay? And that's something that's useful to see on the video. So I urge everybody to sign up for presentations. The 2 slots are next Monday, starting at 12, which means the 6th, or right after the exam, okay, on Friday, okay, which would be sort of, the exam will be Friday from 8:30 in the morning till 11:30 in the morning. If you have, so you can sign up for whichever slot you want. I'm going to pass around the graduate sign-up sheet. Okay. Hopefully, one of these two will not prove to be a hardship. Again, I urge everybody to note there is no grading going to be done on these presentations. So don't worry about it. Don't prepare so that it will interfere with your studying of your exams. That's certainly not what I want. Okay. You only have 5 minutes to speak. This will be strictly enforced, okay? And, I usually have a kitchen bell, and it goes off, and you go off when the bell goes off. But, I'm going to pass around the sign-up sheets. Please sign up. The order that you sign up will be the order in which you speak. But I want everybody to sign up from the beginning of the list on down, rather than signing in the middle of the list. Because some people think, well, if I sign in the middle of the list, everyone will sign in ahead of me, okay? And that way, I won't be the first one to speak. But, if you do it that way, you won't know exactly when you're speaking, okay? And so I think it's better for everybody if they sign up from the beginning of the lists. If I get the lists back and there's a hole before somebody's names, then I know somebody's in trouble, okay? Any questions about the projects? Okay, I'm going to pass them around the sheet with a pen. I expect to get both of them back at the end of the room at the end of the class. Okay, so here, why don't we go pass these around? Okay, any questions about the graduate projects, first of all, before we get any further? Okay, any questions about the undergraduate homeworks or graduate homeworks or anything like that? Okay, question? When do you pick up the homework 5s? The answer is when they're graded, but that might likely be very close to the exam date. What I'll try to do is we'll try to make an announcement on the web page when it's available, and I'll throw them outside my office in a pile, okay, when they're available. But I can't really make much guarantees about when that is. Okay, any questions? The bigger question is probably all about the final. What's the story of the final? It's held Friday, 8:30 till 11 in the morning. Sorry about that for late morning people. The room will be Old Chemistry 116, is what we were assigned. Okay, so the final will not be videotaped. Okay, the final exam will be a lot like the midterms. Okay, the difference is going to be, of course, that it's a comprehensive exam. So there will be some of the exam material will be from the first exam. Some of the exam material will be from the second exam. Some of the exam material will be from the stuff we've talked about since the second exam, which is mostly NP completeness. Okay? There will be something like 6 to 8 problems on that exam. Okay? There will be something like 1 problem that's just for the graduate students. Okay? That will be included in the something like 6 to 8. So it's still somewhat vague. I will guarantee you at least one problem on each of the following topics. Okay? There will be at least one problem on the big O notation, okay, and its implications. Okay? There will be at least one problem related to sorting and searching in some sense. Okay? There will be at least one problem that is a dynamic programming problem. Okay? That is a graph algorithm problem. Okay? And there will be at least one problem that is on NP completeness. Okay? And so in a world where there's only 6 to 8 problems, I've basically told you what's going to be on the exam. Okay? So it should be easier to study for. Actually, how do you study for an exam like this? Again, it's open books, open notes. It's like the other exams. Okay? The best way to solve it is to go back and look at problems. Try to solve the problems that may have been on your homework or something like that. Okay? Maybe go back and check the solutions in the library if you're inconsistent sure with these things. Go back and try to figure out why the solutions are. If you take a look at the problems I've given on past exams, you'll notice that once you actually have the right idea on the answers, okay, you'll find that my answers are usually fairly simple on the problems. You know, my hope is that I give problems that someone who understands what's going on won't have too horrible a time, you know, doing the exam. So I'm looking for mostly ideas more than I'm looking for sort of people copying things from the book. Okay? And so maybe the right thing to do is to go back at these problems and look back and try to ask yourself when you go through them again, what was the idea? How would you have come up with this idea? Okay? You know, why was depth first search the right thing to do here? Okay? Why was dynamic programming the right thing to do here? Okay? And try to learn these kind of things. Okay? Which are hard. Okay? I'm not going to tell you that that's easy skills to develop, but those are the skills that you have to develop in order to sort of do well on the exams. Okay? But the exams will be comparable to what we've had so far. Okay? Any questions about the exam or what's going to be on the exam? Okay? Again, open book, open notes. Anything else concerning the exam? Okay, very good. So far, okay, that's good. Let's then move on to material today. The stuff that I'll talk about today, let's say up to maybe the up to the approximation algorithm stuff I'll talk about, will be fair game on the exam. If I get beyond the approximation algorithms, then that's not fair game. Okay, and you'll see what that is if we get up to it. Okay, any questions? Okay, so what was the problem of the day? The problem of the day asked for give an efficient, greedy algorithm for finding an optimal vertex cover of a tree efficiently. Okay, so what was the question? Okay, we've seen in past classes that vertex cover is a hard problem to solve on graphs. Here they're asking for a fast algorithm to solve vertex cover, but it's limited to trees. They want a linear time algorithm for trees. And the fact that vertex cover is hard in general has nothing to say whatsoever about whether it's hard on trees. All it says is that it's hard for some set of graphs. And trees are usually very nice, simple graphs. So usually they have fast algorithms on trees. In particular, what was the vertex cover? A vertex cover was the smallest set of vertices, such that you get at least one vertex on each edge. Well, what's a tree? A tree is something that doesn't have any cycles. Okay, so every tree looks something like this. Okay, and the key factor of trees is that trees have leaves. A leaf, remember, was a vertex that's only adjacent to one other vertex. Okay? Now, what happens if you take a leaf from a tree and delete it? What do you have left? If I take a tree and I delete a leaf, what do you have? Still have a tree. It's just a smaller tree. So let's think, the way that I would think about it, well, the thing that's special about trees is trees have leaves. What's true about a leaf? Well, you've got this leaf vertex, which is adjacent to one other vertex. How can we cover that edge that touches on a leaf? We have two choices for this edge. Which vertex we would want to pick to cover it? We could pick the leaf vertex or the neighboring vertex. the non-leaf vertex. Is there ever any reason why we would be better off picking the leaf vertex than the non-leaf vertex? I claim no. If you pick the leaf, if you pick the non-leaf vertex, what do you cover? That same edge and some other things. Okay? So since the stuff you cover here is a strict superset of what you cover there, it can't ever hurt you to pick the non-leaf edge vertex of every leaf edge. Okay? And so the algorithm that I would do is basically one. Okay? You do a depth-first search, identify every leaf. When you get to anything that's a parent of a leaf, okay, you delete that. Okay? I mean, not delete that. You label that to be a, what do you call it? A vertex in the cover, and then delete it, because you'll now cover, if I pick this vertex in the cover, I now know this edge, and this edge are all taken care of. I now backtrack, continue my depth first search, having deleted this part of the tray. And now look for minimum cover on the rest of the tray. And so by doing a depth first search and doing the proper bookkeeping, it should be clear that you can pull off the non-leaf vertices, okay, and trim them, and then pull off the new leaves. Look at the new leaves after you've trimmed the tray. Any questions about that? Okay, that shouldn't be too complicated. Okay, and finally, when you finish doing the trimming, you have a tree that looks like this, where you've got two things and both of them are leaves. If so, you pick any one of the two. It doesn't really matter, because everything else is covered. Any questions? Okay, very good. So what are we up to now? Last class, the last several weeks, we've seen how to prove problems NP-complete, prove problems prove problems hard, in the sense that there's almost certainly no fast algorithm for it. Okay? Now, if we think back to the very way we introduced NP-completeness, okay, which, remember, you could go into your boss and say, look, I can't do the job you want me to do, but neither can anybody else. Okay? That will protect your job in the sense that the boss will not fire you and replace you with somebody else. But it doesn't make the boss happy, because the boss still has a job to do, okay? And all you come back and say is, it can't be done. In real life, you still have to deal with complete, okay? Maybe the traveling salesman problem is hard, but if you're working for a company that's manufacturing circuit boards, you still need a way to go back and solder all the points. And maybe it's hard to find the optimal tour, but you've got to go back and find some kind of a tour, okay? So there are two main options that people have once you're dealing with NP-complete problems. One option is to try to find an algorithm in the average case, okay? Maybe in the worst case it's very, very bad, but usually it's pretty good, okay? Like, for example, earlier this semester we worked on the bandwidth problem. For certain graphs, your programs may have been extremely fast, okay, even though in the worst case they were bad. So it may be that, for example, the kind of graphs that you're interested in, okay, in fact, some algorithm that's not provably good thing to do. To come up with an algorithm that you can prove always gives you the right answer and usually runs fast. Okay? Far more often, the solution to dealing with an NP-complete problem is to try to use some kind of a heuristic. Okay, what is a heuristic? A heuristic is an algorithm that doesn't guarantee you the right answer. Okay? It gives you something that you hope is close to the right answer. It's kind of a rule of thumb. Okay? And that although the theory of NP-completeness says that for a hard problem, it takes exponential time essentially to find the exact answer, there's nothing in the theory of NP-completeness that says that it's hard to get to something that's almost the exact answer. Okay? And sometimes by using a algorithm that's sort of more a rule of thumb, okay? You won't necessarily get the optimal answer, but you can come close, okay? Sometimes your heuristics are sort of just ideas, okay, and they don't guarantee you anything about how good your solution is. But the most interesting heuristics are ones where we can prove that the answers that you get are never too bad. Usually this semester we've looked at algorithms that in the worst case always give you the right answer. When you're analyzing heuristics, what the hope is to get a heuristic that you can prove that maybe it doesn't give me the right answer, but it's fast and the answer can never be too much worse. Okay? That's a provably good heuristic, and that's what we would really like to see. Okay, any questions about what these two options are? The first option is to sort of hope for an algorithm that's usually fast but always correct. The second option, the heuristic option, was to try to find an algorithm that's always fast and usually close to correct. Okay? And in practice, this is usually the better one. Okay? Any questions? So let's look at it as an example. Let's look at a problem we've seen several times. Vertex cover. Finding a vertex cover of a graph we've proven is hard. Okay? Vertex cover in general. Okay? The vertex cover problem, again, trying to find the smallest set of vertices such that every edge touches one of those vertices. Okay? It's NP complete to find the optimal cover. However, what's interesting is a very, very simple algorithm can get you an answer that's at most twice as bad as the optimal cover. Okay? So let's think about it. Suppose I give you a graph on n vertices. What is the smallest possible cover you could hope for on a graph on n vertices? Okay? 1. You could end up with a graph that looks like a star. Okay? If your graph was a star, in fact, the optimal vertex cover would be just picking that one vertex, correct? Now, if you run a heuristic on it that guarantees you a solution that's at most twice optimal, it would say that if you ran it on this graph, I'm going to give you a cover that's either 1 or 2 in size. Okay? For some other graphs, let's pick a graph like this. Suppose we have a cycle on n vertices. What's the size of the optimal cover on that? Something like n over 2 vertices. Okay, because if you pick every other vertex, you'll cover all the edges. If I ran my heuristic, it gave me a solution that's within twice optimal. It would give me an answer somewhere between n over 2 and n. Okay? So what's interesting is we can guarantee ourselves, okay, a good cover with the following strategy. Let's start out with the graph, okay? And let's say that the graph originally has some edges in it. What we're going to do is at random pick an edge from that graph. Okay? Which edge doesn't really matter, but it's an edge from that graph. We're going to take both the vertices adjacent to that edge, okay, and stick them into the cover. Then delete any edge that's adjacent to it, okay, either of those two vertices that we just added. Okay? That's going to add 2 vertices to the cover and delete a certain number of edges. If we keep going through multiple iterations of this, eventually all the edges are gone. Okay? So any questions about that heuristic? Let me just show you an example just so people can see sort of what's going to happen here. Okay? Here's a picture from the book. Here is an input graph. We could start out here and pick an arbitrary edge in that graph. Let's say this one. Our vision is that we will put this vertex and that vertex in the cover. Once we have those vertices in the cover, this middle edge is clearly covered. This edge is covered, this edge is covered, and this edge is covered. We can delete them from the graph, and now we have a smaller graph. Pick some arbitrary edge from this graph, let's say this one. We add this vertex and this vertex to the cover. That deletes this edge and this edge. We're finally left with one edge. Okay, pick both endpoints of that edge. Okay. So in the final graph here, this was our graph. This was our vertex cover. These vertices, shaded vertices. Is that vertex the smallest cover of this? Is that cover the smallest cover of this graph?
Why was that the vertex cover? We always pick two.
Okay. No. What was the point? Oh, okay. Excuse me. Sorry about that. You're right. Let's start back here. Which vertices did we pick? We picked this vertex, this vertex, this vertex, this vertex, this vertex, and this vertex. Yeah. Correct? Is this a minimum vertex cover of the graph? No. Why? Well, for example, we could actually, it's not even a minimal vertex cover of the graph, in the sense that we could delete this vertex without penalty. Correct? What? You can delete this one. You could also delete F without punishment. So clearly, by deleting these two, you get an even smaller cover. Okay? In fact, the claim is that a vertex cover of size 3 actually exists on this graph. In fact, if we just picked edges, vertices A, C, and D, this would in fact cover all the edges, right? So in fact, there exists a cover of size 3. Our algorithm gave us a cover of size 6. But what's the problem? Okay, it's not a great cover here, but it's still within twice optimal. Okay, and that's the guarantee that I'd like to claim this heuristic makes. Okay? Any questions about what this algorithm is doing? Okay, you may not believe my twice optimal yet, but that I'll convince you of in a few minutes. Okay, any questions about what the heuristic is doing or how it works? Okay? Now, it should be clear that this heuristic is a very fast heuristic. Why? How much time would it take to do this thing? Okay? Well, if you did some kind of an adjacency, had an adjacency list, okay, it should be clear that you can sort of traverse the adjacency list, find an edge. Once you find an edge, go and delete those two vertices that are adjacent to it, and all the edges associated with that. Okay? Every edge from the graph is only going to get deleted once, so the total time spent deleting things is going to be time proportional to the time creating it, which was linear. So it should be clear that this can be fast. Okay? It should also be clear that this vertex, that this heuristic always produces a vertex cover. Why is it true that the set of vertices we pick is always a vertex cover? Because we're deleting all the edges from the graph eventually. And under what conditions do we delete the edges from the graph? Only if we have picked those two endpoints for the cover. So any edge that we delete has to have at least one vertex in the cover. Okay? And we eventually delete every vertex, every edge. So my claim is this means that we have to end up having a vertex cover. Any questions about that? Okay? How many people believe that? And is there anybody who doubts it? Nobody. Okay? But why is this vertex cover that I give you a good vertex cover? Okay? First thing I'd like to claim is that any cover, okay, uses at least half as many vertices as this. Why is this? Think of all the edges that I pick. Okay? Think about how did I go about doing this. I picked a pair of an edge and an edge from my cover and both those vertices adjacent to it. I then deleted anything else before selecting a next edge in my graph. Okay? Is it possible that the edges that I use to select my pairs of vertices, that any of those edges shared an endpoint? Okay? Remember how the heuristic went? I picked an arbitrary edge, added those vertices to the cover, and deleted all adjacent edges. So really what this algorithm is doing is picking edges, pairs of vertices that correspond to edges. Is it ever possible that any of the two edges that I pick okay, share a endpoint? No. Why? Because what did I do after I picked this edge? I immediately deleted any edges that were adjacent to it. Okay? So one thing that I claim is by doing this, the edges that I pick have to have the property that no two of the edges touch each other. Right? So if this was my what do you call it? If this was the paper, the graph I ran my data on, these were the vertices I picked for my cover, okay? And it was based on these 4 edges. What would a minimum vertex cover of just these 4 edges be? Okay, if I ask for the minimum vertex cover of just these independent k edges in my here, how many vertices do I need to cover just those edges? K. Okay? If I add any more edges to the graph, is that going to increase or decrease the size of the minimum vertex cover? It's going to increase it. If I add more and more edges to it, okay, I have to now make sure I cover all the extra edges. So my claim is an optimal vertex cover on a subset of the edges, or no greater than, the optimal vertex cover on all the edges. Okay? How many people believe that? How many people don't believe it? This is a simple thing to say. Okay? Adding more edges gives me more work to cover. Okay? So what am I saying? All these edges, these 4 edges here, were edges in the graph. An optimal cover of these edges, okay, is basically one cover, one vertex per edge. If I take 2 vertices per edge, that's at most twice the optimal cover for just these edges. Okay? And yet I cover all the edges in the bargain. Okay? So what is my chain of reasoning here? Okay? I originally start out with my graph G. Okay? From G, I end up coming out with K disjoint edges. Correct? My claim is the optimal cover of just these K disjoint edges, okay, is equal to K. Correct? My claim is the optimal cover, let's just move this thing up here, the optimal cover of G is greater than or equal to the optimal cover of this, which is equal to K, correct? So that tells me that the optimal vertex cover of my graph has to be greater than or equal to G, greater than or equal to K, correct? What is the size of the cover that I'm actually producing with this strategy? I'm taking 2 vertices for each disjoint edge I create. What's the size of my cover? 2K. Why? Because what am I doing here? I start out with the graph. I pull off K edges. For each of these edges that I pull off, okay, is my sort of central pull off, I'm claiming both vertices for the cover. So my cover is going to be twice the size of the number of edges that I pick in the course of this algorithm. Okay? What I wanted to claim was that any cover of the graph, okay, has to be at least as big as one vertex per these edges, because all these edges are in the graph to start with. So to just cover these K vertices edges involves K vertices. In fact, by picking both endpoints, I cover every vertex in the entire graph, every edge in the entire graph. So that means that my optimal vertex cover had to be at least as big as K, and the cover I picked was 2K in size. Therefore, the vertex cover I picked had to be at most twice as big as the optimal cover. Okay? And that's sort of the punchline. How many people don't see it? Okay? How many people do see it? Okay? I reversed the order of that, so I don't know if everybody caught that. How many people don't see it? Okay? Everybody claims to see it. So that's good. Okay? What's interesting about this, though? The tactic here is really kind of amazing. Okay? That I came up with a lower bound on the optimal solution in terms of this matching. Okay? And then use that lower bound to describe the solution I actually got. That's how I was able to prove some property to this thing. Okay? And how come this heuristic always gives me twice optimal? Any questions? Okay? There's some interesting things to notice, okay, about this heuristic, which holds true for provably good heuristics in general. This heuristic was very simple, okay, but it was not stupid. Okay? And there's a big difference here. A lot of very, very simple heuristics cannot make the same claim that this one does, that it always comes up with the best possible, with something that's within twice optimal. Can somebody come up with another heuristic for doing vertex cover? Okay? That seems maybe more sensible than the one I just picked. Yeah.
Sort all vertices by degree.
Okay, sort all vertices by degree.
Then pick the one with the highest degree first.
Right.
And delete all the edges and adjacent vertices.
Okay.
And then the next.
Okay, so one heuristic was some kind of greedy thing. Maybe like pick the vertex that covers the most edges. Okay? And then delete those that vertex and then recur. Okay? That one, what will that give you? Actually, I don't remember offhand. That actually is not an incredibly stupid heuristic. That one will actually either give you, I think that might give you a factor of 2 approximation also. Or it might be a log n factor, a closely related problem called set cover. That will give you a log n approximation for, not a factor of 2. For vertex cover, which is simpler, I think it does give a factor of 2. But what would be an even simpler heuristic of the type that I was trying? Okay? Remember, what did I do? I picked an edge from the graph. I said claim both of those endpoints and throw them into my cover. If you think about it, that doesn't seem like a smart thing. Why do I need both endpoints to cover that vertex, that edge? Wouldn't I have been better off just picking one of those endpoints, okay, and then throwing that one out, okay, instead of picking both of them, because I'm in some sense wasting coverage. I'm doubling coverage on every edge that I pick. Well, that would seem like a smarter heuristic. But let's think what happens if we do it on a star. Suppose we pick an edge of the graph, like this one, okay? And now we're forced to pick between this vertex and that vertex. What happens if we decide to pick, well, let's say we pick that vertex. Okay, now we've covered this edge. Now we've got another edge we pick. Let's now pick between them. Maybe we'll pick this vertex. Maybe we'll pick this vertex, this vertex, this vertex, this vertex, this vertex. If you insist on picking one of the two, and you always pick the wrong one, you could get a heuristic that could give you a solution of size n minus 1, where the optimal answer is a vertex cover of 1. So here's an even simpler heuristic, okay, which seems to make sense. But if you're very unlucky about which one you pick, okay, you could still get burned. There's nothing provably good about that heuristic. If you cover both of them, we can prove something about it. But covering one of them, you can get screwed if you're unlucky. Okay, question?
The thing about this is that in this situation, the inverse of your vertex cover is the optimal vertex cover. And so what you can do is that you can modify this algorithm such that if the number of vertices in your vertex cover exceeds half,
okay. Okay, so what you're now proposing is a heuristic where you'll say, what happens if instead of saying, well, look, okay, this one cover I had was good. Maybe if I take everything that was terrible, but in fact the complement of my cover was good. Well, that won't work for a couple of reasons. First of all, it's not obvious that the complement of a vertex cover is a vertex cover. Because if your vertex cover did in fact have both edges of an endpoints of an edge, okay, then in fact it would no longer be a cover if you complemented it. Okay? Here for a tree, that proves to be a safe thing to do. Okay? But in general, the complement of a vertex cover is not a vertex cover. The other problem with that is to see that even if it was, your heuristic could still do very badly. Because suppose, let's say, instead of guessing unluckily, well, I have a choice of picking this one or that one, I'll pick this one. What if I guessed wrong the first half of the time and then guessed right? So that I ended up getting half of the outside vertices and the center point in my star, in my cover. If I pick something like this, okay, I could just as easily have ended up guessing this. And the complement between this and itself is both of them are very large. Both of them are n over 2 times the optimal. So that wouldn't guarantee me a size bound, okay, even in this case. Yes? Okay. The other heuristic which comes to mind fairly quickly is, again, what if you pick the largest degree vertex? Okay? And there are results for that. I believe it's actually true that if you always pick the greedy vertex, okay, you will in fact cover it with a factor of 2 approximations. Okay? But that's something that's a little harder to show. Okay? But that heuristic will in fact work well for this. But for other problems, it's surprising. That actual heuristic does not necessarily always give you good bounds. Okay? Question?
What if you went through and threw away all of the 1 degree vertices?
What if you went through and threw away all the 1 degree vertices? Okay? Would you then be able to do? There's lots of heuristics you can now come up with. Okay? The interesting thing to see is that it's very easy to make a heuristic more complicated. Okay? In the sense that you can make it look like it's doing smarter things. The trouble is to try to make it just complicated enough that it gets you the approximation bound. Okay? What I can tell you now is this was a very, very simple strategy to approximate vertex cover within a factor of 2. Okay? There is no known heuristic that does much better than a factor of 2. Okay? Even though this does stupid things in certain cases, that maybe you can say, well, look, in this case, okay, I can fix it up. In fact, as far as a guarantee goes, this is, I think, about as good a guarantee as you can get. Okay, a vertex cover is an interesting problem because there's lots and lots of different heuristics for it. Something that's been studied quite a bit. Okay? So what's the take-home lesson here? The key idea to proving something about a heuristic is to come up with a lower bound on the optimal solution. Okay? It's very, very easy usually to come up with some kind of a heuristic that will give you some kind of a cover. Okay? Or for the traveling salesman problem, some kind of an ordering. Okay? The trick is you want to prove that this ordering is almost as good as any possible ordering. And the key to doing that is to come up with a lower bound on the optimal solution. The way we did this for the vertex cover problem was we found out that if we took a matching, a subset of the edges that didn't touch each other, that had to give us a lower bound on the optimal vertex cover. And then came up with our answer in terms of that. Okay? Any questions? Question? Wait, you mean which suggestion? The you mean about trimming off edges, things of degree 1? Well, the reason why that might be bad is not actually on this particular graph, but the reason why it might be bad is for a lot of graphs, there are no vertices of degree 1. Okay, suppose let's say that the graph we had looked like this. Okay, so I had 2 stars that were kissing each other. Okay, which vertex of degree 1 should we delete first? Well, there is no vertex of degree 1. Okay, so on this graph you're stuck. Okay, if you now go through and say, I'll take this as my first edge, and the endpoint of that I'll pick will be this one, you can go through the exact same struggle that you went through before. So that's why that kind of a heuristic makes things more complicated. It doesn't, in the worst case, improve things. Okay? This is kind of a counterintuitive thing. Okay? Question?
Since vertex is the highest degree, worked on all the examples we had so far.
The vertex, the thing of highest degree works well on all of these. You're saying, in fact, that if you always pick the highest degree, that it works on all of these examples. Why isn't it true, now you're asking, that always picking the highest degree doesn't give you the optimal solution?
That I probably would.
Okay, the reason why you know that that doesn't work is that can be done in polynomial time. And if the greedy heuristic always gave you the optimal solution, we would just have a polynomial time algorithm for an NP-complete problem, and we would be famous. Okay, and you don't get famous that easily. Okay? Any questions about that? Okay? In fact, like I said, the greedy algorithm on this problem happens to always work well. Happens to work well. But for most problems, that's actually not, for a lot of problems, that's not necessarily true. The final thing to say is that often these heuristics that we use are brutally simple. Okay? Like taking both endpoints of the thing. It might pay afterwards to do some kind of a post-processing cleanup. Like to go back to see whether or not we have a vertex that isn't covering anything that hasn't already been covered. Okay, and then delete that one. So on the previous example we looked at, you know, it wouldn't kill us to go back through our cover and say, look, this edge is already covered. We might as well delete that from the cover. And might as well delete that from the cover. Okay? But in the worst case, it doesn't improve our bound. Okay? Because we're looking for this approximation ratio. Any questions about that? Okay? Heuristics, provably good approximation algorithms, is really one of the exciting areas in algorithms today. Okay? Because, you know, for a long time, people were trying to solve problems. Then NP-completeness came along. And then people said, well, I'll prove that it's, you know, I can prove that my problems are hard. But then people said, well, look, maybe you can prove something good about inexact answers. And approximation algorithms became very popular. Okay? And now people are getting to the point where there's problems that they're finding that are hard to approximate. Okay? And now people are starting to prove some problems not only can't you come up with the optimal answer, but in fact you can't even come close to the answer in polynomial time. And that's actually a very exciting area in theoretical computer science these days. Okay? Exciting enough it made the New York Times front page a few days of the science section a few years ago. Okay, any questions? Okay, let's look at another problem for which a approximation algorithm holds. Okay, and this is our friend the traveling salesman problem. Okay, again we've seen the traveling salesman problem lots of times. Okay, you have a set of points in the plane, and you'd like to visit all the points in the plane using as short a tour as possible. Okay? This problem, the traveling salesman problem, we didn't really prove it was hard, but in the book you know that we've talked about, there was a proof that the Hamiltonian cycle problem was hard. Hamiltonian cycle problem and the traveling is really a special case of the traveling salesman problem. So traveling salesman problem becomes hard from that. Okay? And in general, the traveling salesman problem stays hard even if the cities, all the distances between pairs, correspond to the Euclidean distances of points in the plane. Okay? So what's true about Euclidean distances? All distances in any kind of a reasonable distance measure satisfy something called the triangle inequality. What is the triangle inequality? It says that the distance of the shortest distance to go between points U and W is less than or equal to the shortest distance to go from U to some point V plus the distance from V to some point W. Okay? In a graph satisfying the triangle inequality, you have the situation where it pays, okay, to take the direct route if a direct route exists. Okay? Rather than to take a detour through something else. Okay? Now, in most problems, okay, the Euclidean distance, or this triangle inequality, holds fairly naturally. Okay? So, for example, if we had a map of cities in the United States, and we had the shortest path distance between any 2 points, defining our edge weights, that graph would satisfy the triangle inequality. Correct? Okay? Most reasonable distance functions would satisfy that. Okay? But not all. Okay? For example, I've been trying to book plane reservations recently. Okay? And one thing that you could imagine is, if I want to fly to certain places, you could imagine a graph where the vertices correspond to airports. And the weight of an edge between two sites is the cost of flying between there. Okay? Airline distances prices do not satisfy the triangle inequality. Okay? Sometimes the cheapest way for me to fly from here to Chicago might be to go through Mexico or God knows where. Okay? Even though the cost of flying to Mexico may be more than the cost of flying to Chicago, somehow the triangle inequality doesn't necessarily hold in certain applications. Okay? I think airfare prices is something one should be convinced of. Okay? But in a lot of applications, the reasonable applications, the triangle inequality is an obvious and natural feature. Okay? Any questions about what I mean by the triangle inequality? Okay? This is a good thing to know about. If you're confused, I'll be happy to explain it again. I don't think I did a good job with that. Okay? Any triangle inequality questions? Okay. What is the point of this thing? My claim is that although the traveling salesman problem is hard, okay, in with points in the plane, we can always come up with an approximation that's close to the optimal answer. Okay? Why is that? Well, if we're going to come up with a provably good approximation algorithm, the thing we have to start out with is a lower bound. Okay? We need to come up with some kind of a lower bound on the cost of the optimal tour. Okay? My claim is the following is a lower bound on any traveling salesman tour, okay, where the triangle inequality holds. Okay? My claim is the cost of a minimum spanning tree in that graph is going to be less than that of the optimal TSP tour. Okay? So here's our graph. Here is, let's say, a minimum spanning tree on that graph. My claim is the weight of this minimum spanning tree will be less than that of any traveling salesman tour that visits all those points. Why is that? What happens if I take a traveling salesman tour and I delete one edge? What do I get? Okay, I get a path. Okay? And what is a property of a path? A path is a tree, correct? So what do I know about the minimum spanning tree and this path? The minimum spanning tree, remember, was the spanning tree of minimum weight, okay, in the entire of all possible spanning trees of that graph. If I have a cycle in my graph that visits all the vertices, and I delete one of those edges, what I've left with is a path that visits all the vertices, which is a spanning tree of the graph. So any spanning tree has to be greater than or equal to in weight than the minimum spanning tree. In the optimal traveling salesman tour, okay, it has to consist of a spanning tree plus one edge, which clearly is going to weigh more than just that spanning tree. My claim is, I've just proven that the minimum spanning tree is a lower bound on the cost of any traveling salesman tour. How many people get it? How many people don't get it? Okay? Nobody is willing to admit they don't get it. Okay? So what does that mean? That means that I now know that if I do a minimum spanning tree, I get a lower bound on my tour. But now I need to construct a tour. Okay? Suppose, let's say, we were allowed to visit each edge more than once. How would we convert our minimum spanning tree into a tour? Okay? Our minimum spanning tree connects every single edge, all the vertices together. Okay? If we were to do a depth-first traversal of that minimum spanning tree, okay, and walk over each edge twice, that would give us a tour where we were allowed to visit each vertex more than once, right? What would be the order in which we would visit these edges in a depth first search tree? We'd start out from here. We'd go down to there, right? From here, we say there's nothing else that follows. Back up. Go back to that vertex. Now we start doing a depth first search from here. Go down. Go down. Go down. Nothing else coming from here. We would back up to this vertex. And then go down. And then back up to that vertex. And go back. Go down. Go up. Go back. Go down, go down, go down, go up, go down, go up. Go up, go up. If we do that kind of a depth first search tour, how many purple lines do I have associated with each edge? Exactly 2. So if I were to walk to each, do the walk this way, I would be visiting every edge in my minimum spanning tree twice. This gives us a way to visit all the vertices, okay, and get back home in weight twice that of the minimum spanning tree. Okay, how many people believe that? Okay, so the traveling salesman who's willing to see a city more than once, by doing this algorithm, would manage to guarantee themselves a tour of more than twice that of the optimal tour. Correct? But is there any way we can arrange for them to not see cities more often? Is there in some sense some waste on this tour? Okay?
If the graph is, if we create a transitive closure such that when you're backtracking, you skip all the interim nodes which only have, which are only there, and then just bypass it.
Right, so the question, the answer is, what if we think about the full graph instead of just this minimum spanning tree? Okay? In fact, there's other edges in the graph. Okay? We could in fact take, since really what we're doing is we're starting out from this one vertex, going to here. Our next goal is the next unvisited vertex. Okay? What we would really like to do, instead of going bop, bop, we'd be much better off taking the direct shortcut to the next vertex we want to visit. Okay? If we do that, are we going to make the tour longer or shorter? Potentially shorter if the graph observes the triangle inequality. Because if in fact it is cheaper to go between here and here directly than it is to go through some intermediate point, okay, then in fact it's clear that taking these shortcuts can't increase the cost of the tour. This is exactly the triangle inequality. The distance from here to here is less than that of going through some intermediate vertex. So we could use the triangle inequality to cut short our tour between any place where we want to go next. Okay? And thus guarantee ourselves a tour that's no longer than that of twice the minimum spanning tree. And if we've done that, that guarantees us that we will come within a factor of 2 approximation of the size of the minimum spanning tree. Okay? Any questions about that? Okay? This is actually kind of a neat idea, if you stop and think about it. Okay? And it's actually kind of amazing that we can come up with a factor of 2 approximation. Can somebody else give a different idea for a heuristic for the traveling salesman problem? Okay? How might you otherwise want to do this? Okay? One idea might be to say, well, pick the biggest distance, pick the shortest distance between 2 points, and start from here, and maybe always wander to the closest point. If you do that, you might end up much, much worse than twice the optimal. Okay? You could end up with something that's log times the optimal. Okay? So that simple greedy heuristic does much worse, for example, than the minimum spanning tree heuristic. Okay? Another heuristic might be to match the vertices up somehow and wander around there. Okay? But again, that does worse. Yes, question?
Can we do that using shortest path tree?
Could you use that using a shortest path tree? Well, you could use shortest path tree if you could prove that shortest path tree was weight less than or equal to that of the minimum spanning tree. Why did we use, oh wait, no. We were using the minimum spanning tree here because we could prove something about it. We could prove that it was strictly less than that of the optimal TSP tour, correct? Certainly if you took the shortest path spanning tree and did the same kind of operation, you would get a tour that's length is at most twice that of the shortest path tree. In order to complete your argument that that gives us a good approximation for minimum for TSP, you'd have to now show me that the shortest path tree is in fact a lower bound on the size of the minimum spanning tree. And that I don't have any reason to believe, okay, that in fact the shortest path between all nodes, okay, is, it's an interesting idea, okay, but now what you've got to prove to me is that the shortest path tree that connects one vertex to all other vertices is in fact has a total weight of less than that of an optimal tour. If you can prove that, that's good. Okay? But I don't see any reason to believe that that's true. Okay? Although it might be. I don't see any reason to believe it's not true offhand. But without a proof, it doesn't mean anything. There's no guarantees. Okay? Any other questions? Okay? So a lot of the heuristics, for example, you may remember way back to the beginning of the course, the first day of class, okay, I gave you a couple of different heuristics, a couple of ideas for how you might solve traveling salesman. Okay? Neither of them involved taking minimum spanning trees. Both of them seemed logical, like the greedy one, go to the next closest. Okay? In fact, if you did that, you might end up with a tour in the worst case that's much worse than the optimal tour. Okay? Whereas, if you use this minimum spanning tree heuristic, you're guaranteed something within twice optimal. Okay? Any questions? Now, another question would be, how close to optimal is this? Maybe there is a heuristic that does better, okay, that can come closer than a factor of 2 times optimal. Okay? For a long time, there was a heuristic called the Christophanides heuristic that would guarantee you a solution that was 3/2 times optimal. Okay? It was slightly more complicated than the minimum spanning tree argument. Not so much more complicated. Okay? But for a long time, that was actually considered to be the best possible approximation for a minimum spanning tree in the plane, okay, or with under TSP distances. That apparently ended about 2 weeks ago, okay, where somebody, a guy named Sanjeev Arora at Princeton, just came up with an approximation algorithm which comes within a factor of 1 plus epsilon times optimal for any epsilon you can choose. Okay? So if you want something that's going to give you a traveling salesman tour, okay, his heuristic will give you, you say, I want a traveling salesman tour that's within a factor of 1.2 times optimal. By plugging in an epsilon value of 0.2, his heuristic can do it. If you want a traveling salesman tour that's within a factor of 1.000000001 times optimal, you plug in epsilon for that, his heuristic can do it. What's the catch? The time that it takes is proportional to, in some way, this value of epsilon. So the smaller you make epsilon, the longer his algorithm takes to run. So it's not like a free lunch. He says that you can't just sort of plug in a value of epsilon equals 0 and get the optimal tour. Okay? But what it does say is that there's an arbitrary, if you're willing to spend polynomial time, any constant factor you want, you can achieve within polynomial time. Okay? So in fact, the traveling salesman problem, which is this famous hard problem, okay, for the special case where points lie in the plane, which is a reasonable special case, okay? It's what motivates trying to find the shortest route in distances and in routing robots and things like that, okay? In fact, you can come close to the optimal. And like I say, this is a result that happens to be only a few weeks old, okay? And kind of, I think, is an appropriate place to think about things, so that even though the fundamentals of algorithms sort of stay the same, in fact, there are new results all the time, okay? Even on such fundamental problems, problems that people had looked at for a long, long time. This previous bound of 3/2 times optimal, I believe, was done in 1976, okay? And now we're in 1996. So it took 20 years to go from here to here, okay? But lo and behold, progress still be made. Yes?
So this gives also the same bound more or less for all other problems that we can reduce to traveling salesman.
This would give, well, now the question then goes, does an approximation bound on traveling salesman, does that imply anything about approximation bounds on other problems? After all, we could use our reductions for NP completeness to convert other problems to traveling salesmen. Okay? Is it possible that maybe we can use this approximation algorithm to give us approximation algorithms for other problems? And the answer is you have to be very, very careful about the reductions that you do. Looking at the reductions we've talked about in here, all we worried about was preserving the correctness. That the answer to here was yes if the answer to that was yes. We didn't say that if the answer to this was almost yes, the answer to that is almost yes. Okay? If we could, in fact, preserve the almost answers as well, then we could use that kind of a reduction. And so there's been a lot of work, again, in trying to look at this question of proving problems hard to approximate. The way that people prove problems hard to approximate is in some sense analogous to what we are doing with proving problems hard. You find some problem that you can show can't be approximated easily, and then do a reduction, okay, to show that somehow that if you could approximate this guy closely, you would approximate the other guy closely. Okay? But things get a lot more delicate when you talk about approximation bounds rather than exact bounds. Okay? Any other questions about approximation algorithms? Okay? Very good. Okay. What I'd like to conclude is something that is another problem where, which I think is important in algorithms. Although this won't be on the final. Okay? So if you don't want to take notes on this, I guess you don't have to. But we've talked a lot about trying to find exact answers to problems. Okay? That was the algorithms we looked at, everything before the second midterm. We then showed that it was hard to find exact answers to certain problems. Okay? And starting today, problems you could always come close to the right answer. Okay? But there are certain problems that are very important to solve, okay, where the right answer is not always so clearly defined. Okay? Including one that everyone in this class, hopefully, will at some point try to solve. Okay? The problem is, how do you find an optimal person to marry? Okay? Let's think a little bit about this. Some people may say, is this an algorithm problem? The answer is, of course, this is an algorithm problem. Okay? About that. Okay? And how to convert this into the problem of finding the right person to marry into a well-defined algorithm problem, and then give you the right solution. Okay? So you can go and take this away with you. Okay? What is the problem? Well, if you think about it, okay, during the course of your lifetime, you're going to meet up with a lot of different people, okay, who you might be potentially interested in marrying. Let's say you'll meet N, if you're a man, you're interested in marrying a woman. Find which is the best one to marry. Okay. Now, the problem is, if all these people you met at once, and you could line them up against the wall and ask them questions, there'd be no problems identifying who was the best one. Okay? You go after interview them and you pick the best one. Okay? But what's the problem? Okay? They don't appear all at the same time. Okay? You meet people one at a time. Okay? And once you meet them, okay, you've got to decide them. Do you want to get involved with them? Do you want to get to know them better? Okay? And, you know, when you get involved with somebody, they would be very upset if you tell them, look, I've now gotten to know you. Wait around for a while for me to go check out some other people, okay, and see if I like you the best, okay? The problem of selecting an optimal spouse, okay, is difficult because we don't have complete knowledge at the beginning of the, you know, at the beginning, okay? And we don't either, okay? You meet somebody, you think they're, you know, the first person you get involved with, you meet them, you think they're really great, but you don't know how they compare to what's afterwards, okay? So what is the problem here, okay? In the course of our lifetime, we are going to meet n people, one by one, okay? We're going to try to come up with a strategy that will enable us to say, you are the best one I'm likely to see, okay, at the time that you meet them, okay? And we want to try to maximize the chances of getting the best possible spouse, okay? But the problem is we have to decide to either marry them or reject them once we meet them. There's no going back, okay? I can't put somebody on the shelf, okay? I either have to decide to marry them or let them go, okay? This, I claim, is a fairly accurate model of the situation of trying to get married, okay? It captures certain components of that. Okay, any questions about what the model is or anything like that? Okay? Now, the truth is, of course, that the world, you say, if you knew what order people gave you the candidates, that would solve it. In general, we have to assume that all the candidates, as n candidates, they're all ranked from 1 to n, but any permutation, any ordering of them arriving is equally likely. Okay? And we have to find the best one. So what's the example? Okay? The example would be, suppose, let's say, that we met in the course of our lives, we're going to meet 6 people. Okay? We meet the first one, okay? We don't know that this person is going to be 4th out of all the people we meet. All we know is this person is the best person we've seen so far, right? You can't rate, you know, how good is your first love, okay? You can't tell until you have your second, I guess, okay? So what is the, so at first you only know that the first person is 1. You then meet the second person. What do you know about the second person? Well, this person was ranked better than the first person. You can say, oh yes, good thing I didn't marry the first one, okay? But should I marry the second person I meet? Okay? How do you decide? Okay? Maybe you let them go and then meet the third person, and you discover the third person wasn't as good as the last one, but was better than the first one. So realize what our world is. We're building up a permutation of things that we see, okay? And our goal is to stop at the right place, okay? Does anybody have any proposed algorithms for how do we decide who we stop to pick if we want to end up with guaranteeing the best ones? Okay? How many people here are married already? Okay, well, you guys must have used some kind of a strategy, so there should be some ideas out here. My claim is that a strategy has to look something like this, okay? If you want to guarantee yourself the best possible one, does it ever pay to pick somebody? Would it ever pay to pick this person here, the third person we meet, if we know that we'd already seen somebody better than them? If we wanted to guarantee we end up with the best one or maximize our chances of ending up with the best possible one, would we want to settle for this person? My claim is no. Okay? But my claim is that we won't really get confident about our decision of who the right person is until we've met a certain number of people. So what does the optimal algorithm look like? Okay? The basic optimal algorithm has to be, okay, you sample some fraction of the candidates, okay, evaluate them one by one, and no matter how good they are, reject them. Okay? Then after you've gone through your sampling period, if you want to guarantee your chances of getting up with the best one, okay, what do you have to do? You pick the first person that's better than anyone you've seen before. Okay? that I claim is going to be something like the best possible algorithm. Okay? But what haven't I told you? Okay, if you want to try an algorithm like that, there's one key point you have to figure out. Okay?
Well, how long is the sampling?
How long is the sampling period? Okay? Well, let's think about it. Suppose we didn't do any sampling. Okay? We just took the first person we ever met. Okay? What is the probability that we would end up with the best possible person? Okay? If we think about it, all possible candidates, sets of candidates are equally likely. My claim is that out of the n factorial permutations, we would end up with the best possible person if the first person ranked totally happened to be the first person we met. There's n minus 1 factorial permutations where the first person is in fact the first person in the permutation. So n minus 1 factorial over n, 1 over n is the probability of ending up with the best one. Okay, does everybody agree with that? If we just pick the greedy strategy, where we pick the first one. Okay? In general, what is the idea for how we should sample, though? Let's analyze this. Suppose instead of picking the first one, okay, we sample out of our n people some fraction f. So we sample 1/f of the total candidates first. What's the probability of ending up with the best one? What's the problem? If we make f too big, meaning we sample 90% of the people, odds are we would have already rejected the best one there was. But if we sample too few, our judgment is skewed. Okay? How do we analyze this thing? Suppose, let's say, that we've sampled 1/f of the candidates. Okay? Suppose that a candidate number I plus 1, okay, is the highest ranking person in the first n over f candidate. So now we've got a world where we've got a total of n candidates. There's n over f that we've all rejected on principle. Okay? And now we want to know, what is the likelihood we end up with the best? What is the likelihood that we will wind up with the best possible candidate? Okay? It would be if the best possible candidate existed somewhere out here in the unrejected section. Okay? And if I plus 1, okay, was the best ranked person in the beginning, so long as we never had anybody between here, okay, and the 1 whose ratings were less than I plus 1, we would end up with the best possible candidate. Does everybody agree with that? Or this actually is simpler maybe than I'm explaining it. If we rejected all these people, I'm going to take the best person after that. The situation in which we win is if the optimal person was here, okay, and there was nobody in between here, okay, who was less than I plus 1. Which meant, since I plus 1 was the smallest value in all here, all the numbers 1 through I had to be in the unsampled region. Okay? Thus we know that the only way that we will win is if, out of all the I factorial permutations of the numbers less than this in this second half, if the optimal choice happened to be the first one, because that's exactly the condition under which we end up with the optimal winner. Okay, any questions about that? Okay, how many people sort of see what I mean? Okay, how many people are confused? Okay, so what's the point? We know that there's a 1 over I chance that if let's say we end up with the highest ranking person, okay, in the first part as being I plus 1, there's I factorial possible choices, I minus 1 factorial of them have the optimal person in the optimal spot. So there's a 1 over I probability that that's true. So for every value I from 1 to n, okay, we have to consider what's the probability that the optimal person in the first fraction was person 2, person 3, person 4, person 5. Okay? So for all values of I, the probability that that person, okay, was in fact in the next half. Okay, we had to first that all numbers less than I had to be in the first half. That's what covers here. I has to be in the next half. That's over here. Okay, I mean all the numbers less than I have to be here. The ith number has to be here. The probability that we end up with the right order is 1 over I. When you play around with it, this sum gives you what the probability of winning is. Okay? And by an analysis of this probability, in fact, you can show that the optimal solution comes when you sample 1/8 of the candidates. Okay? So what's the point? You remember in calculus what E was? E equals 2.718. 1 over E is approximately, okay, 0.4. Okay, about 1/3, somewhere between 1/3 and 1/4. What is the lesson here? You should go through the first 1/3 of your projected dating life, okay, and reject them, okay, and then take the first person you get after that, who's better than anyone you've seen, if you want to maximize your chances of getting the best. But what's the problem with this? Okay? Okay? It also gives you a 40% chance that you will not marry anybody. Because nobody, you might have already seen the best person go by. So if you want to maximize your expected chances, okay, then perhaps that opts for a strategy where you select earlier. Okay? Or where as time goes by, you weaken your standards. Okay? Okay? So maybe I'll just grab what I can get. Okay? Bottom line, think about it. Okay? Use whatever strategy you want. Okay? Good luck, and I guess I'll see you guys at the final. Okay, thanks.
What about backtracking?